Variational principles and the foundations of complex fluid mechanics.
Okay, so now I will derive the equations of motion using Hamilton's principle. So this means that I have to compute a critical field for this action functional for any kind of variation of phi, this phi, which is of this form, such that at end time, and this is 0, right? So in order to do that, we first have to fix boundary conditions. So I will first consider the simpler situation of prescribed boundary. Boundary means that phi on the boundary of G is known. Right? So this induces some additional property of on these variations. Delta phi at xt is always 0 if x is in the boundary of G. So this makes easier to compute the equations of motion because I can integrate by part. This is 0 and the spatial boundary of the domain. So doing this, I'm not giving the details because you will see that this is almost trivial. This is 0 if and only if this equation holds. So we have rho 0 x d square dt square phi x I equals I p I x. Let me explain what this is. So this is the time-dependent configuration of the phi. This Pi is called the Euler-Kirchhoff tensor, and it is defined by W G I. So remember that L from the first part, remember that L is of this form. 1 over 2 rho 0 x phi dot x square relative to G dx minus W d phi x other fields dx. So it's clear when I take variations, I have exactly what I'm doing in the usual Hamilton's principle. Derivative of L with respect to phi minus dt derivative of L with respect to phi dot Using this, I first get this part here, when I derive with respect to time, and then when I derive with respect to phi, I take the derivative with respect to this. I integrate by part. I can do that because I have this condition, right? And I get exactly this term, which is the divergence of the Piola-Kirchhoff tensor. Piola-Kirchhoff tensor is the derivative of W relative to this slot here. Right?
Mr. Sign?
No. Integrates both spaces.
Where?
No, it's correct.
Okay. So now, until now, I worked in intrinsic way, and here you can see that I have coordinates. In fact, if I want to write this equation in intrinsic way, it requires more geometry. It is needed to write this equation in intrinsic way. First, I have to replace here d dt squared by covariant derivative associated to the metric little g. And here I have to take covariant divergence relative to the metric big G. But I will not do that because we will soon pass to the spatial representation, which is more useful. So this is just to give an idea. Now, what is this object? This object lives in the middle of the two representations because it has one index material and one index spatial. So for those who know about tensor field, this Pi which has one index up like that is the P of dx I big X I d small x I. This is from T tangent space times tangent cotangent space This is called a two-point tensor. This is just for those of you who are surprised to see two indices of different nature. So these objects exist, and it's known how to take divergence of them to build this thing and to write this equation. So also another useful relation P is the Piola transform of the Cauchy stress tensor. Sigma ij, because this is the one you probably know about. So just to explain this, the relation is this. So if you have two-point tensor, it's more complicated than pull back and push forward. You pull back only the indices you can pull back, not the other one. That's what happened here. The I doesn't move, only the J becomes. So these are two remarks to connect with what you probably know. Okay. Now let's go to free boundary problems. Second case, you have free boundary. With surface tension. So how do we treat these problems using Hamilton's principle? So we add the term minus tau integral over the boundary of this domain, the area with respect to some volume, some metric. Which metric? Phi star G. Add the term to the Lagrangian. So this is a boundary term, right? So the area element associated to the pullback of the spatial metric here, you compute the area of the boundary. What is now the how to say, the constraint on the variations? Delta phi, delta phi only satisfy endpoint condition. We don't have this. No more true, right? Because now you don't have fixed, you don't have prescribed boundary condition, you have free boundary. So what will happen when you compute the variational principle? You cannot integrate by part and cancel the boundary term. Boundary term will remain. They will combine with what you obtain by taking the variation of this term. So I'm writing the variation of this term. Variation of this term. Of this guy. G the epsilon. Epsilon equals 0. So you have the area element of you don't move the metric, you move the configuration map, not in time, but in variations, in epsilon variation. And this is a formula that I will not prove. What you obtain is, I will explain the symbol. Don't be afraid, this is simpler than what it looks like. So what this means? So we have the metric on the spatial metric at the point phi of x, which is variations of delta phi and the normal vector to this phi of B relative to the metric G. So if this is the usual metric, this is simply delta phi x dot n at the point, the same point. But this has to be multiplied by this number. This number is the mean curvature of phi of the image of the boundary by the configuration map. So this means the current free boundary relative to metric G. So now you repeat exactly the same Hamilton's principle, and you get rho 0 x t squared phi x t equals, let me write g t because I already explained what this is, and the remaining terms on the boundary. So you have p dot n equals minus tau curvature. Everything is at point phi of x. So on so do you understand at least the idea, right? We get usual equations plus boundary terms here coming from the fact that the variation doesn't vanish at the boundary, and another one coming from the extra term in the Lagrangian. So since this has to hold for all variations, they are equal, and we get the usual condition in appearing in free boundary problems. So this P, of course, depends on the W that I'm choosing, right? So for fluids, for example, this recover pressure composed with phi equals tau mean curvature, for example. But here I don't specify the specific problem. Pressure equals is proportional to mean curvature for usual. But here this is okay. So now I'm ready to pass to the spatial picture. So this is number 4, variational principle. In spatial representation. So we have seen equations of motion in material representation is equivalent to Hamilton's variational principle. For all delta phi such that this is important for what I'm doing now. Tx always and some other constraint that may depend on the problem you consider. For example, here, no additional constraint, and here, yes, this is prescribed, so you must have this equals 0 on the boundary. Now we want variational principle in spatial variables. So let me recall what are spatial variables. They are on the left. On the right hand side, so you have u, you have rho and little c. U is such that is odd, right? The motion is the flow of the vector field. Rho is the push forward. It's the push forward of the material mass density. Right? We computed this that in this way. This is pi minus 1 x t times the determinant of the matrix of partial derivative. Right. So I'm recalling that
Times dx.
times d.
D unit x.
So I'm recalling that going this way is push forward and going this way is back. So here, since rho 0 is a material quantity, I have to push forward it to get the usual mass density in other variables. And this is in fact not correct, minus 1. Right? And finally, C of xt is the push forward of big G. And I wrote for you the local expression of this in the first part. So first step, Lagrangian. We have to write the Lagrangian in Eulerian variables. To do this, so from now on, we focus on fluids. This means so this is a formula you have. Let me write again. This means L of phi dot equals kinetic energy rho 0 x phi dot dx g x minus internal energy in terms of material variables rho 0 x divided determinant d phi x rho 0 x dx. So this was the Lagrangian of the fluid written in material representation. So the one I wrote this morning when I checked that these two terms are isotropic. So now I have to make these guys u and rho explicit in this equation. So I do a change of variable. Yeah. I'm here. Change of variables. So I have 1 over 2 phi of b rho 0. Here I insert my change of variables is of course x equals phi of dx. I can forget the time now because I'm just rewriting this expression, which is independent of time, in terms of different variables. So there is no time involved, no x. So this is phi minus 1 small x. Right? Here I had phi dot of big X. Now I have phi minus 1 small x. Then this is due to the formula of change of variables, right? Gx minus rho 0 phi minus 1 small x, right? Dx small x. Determinant partial derivative at this point. Rho 0 phi minus x d phi minus 1 x dx. So what do we recognize here? These two, this is simply rho x t. Now this is u, no t for the moment, u of x. This is, so the determinant of d phi at phi minus 1 is 1 over determinant of d phi minus 1 x, right? So this guy goes up, and the whole stuff here is rho of x. Here also. So no surprise. We get 1 over 2 rho x ux squared g dx minus e rho x dx. So step 1 is done. It's rewriting the same Lagrangian in spatial variables. Okay. Now step 2 is the question. I have delta L phi dot, right? L phi dot is the same as that. The question is, what are the variations allowed for U and rho? Because I want to get rid of all material picture. I want to write the Hamilton's principle directly in terms of spatial variables. So this is also a computation, a direct computation. So, for example, delta U of x epsilon of U. But I have to remember that U is phi dot phi minus 1 x. Do you agree with this? This is equivalent to U. Okay, so I'm starting computation. Derivative relative to epsilon. We first take the derivative of the first function. But here t is important. Plus, we freeze this guy and take the derivative of this. So this is d phi dot at this point in the direction d epsilon. Epsilon equals 0, phi epsilon.
Equals 0, the first one.
Okay? Right, now I have to know how to compute this. So if I have delta phi, how do I get delta phi? So I know that this is the identity, right? So this means that delta phi of phi minus 1 x plus d phi x delta phi minus 1 x
0.
Second line is 0. Second line.
First one is 0.
Oh yeah, right. Okay, so from this I obtain delta phi minus 1 x equals minus d phi minus 1 x delta phi minus 1 x. So I can insert this expression here. I have delta phi dot phi minus 1 x t plus d phi dot at the point phi minus 1 xt in the direction this, so there is a minus d phi minus 1 x delta phi minus 1 x. For simplicity, I assume that t is inside the phi, just to don't have too many notations. Now, this term, what I would like to have is this. You will see in a moment why. I want to have the dot outside. So since I impose this, I have to correct the formula. And I'm giving the answer. This is minus d delta phi minus 1x dt phi minus 1x minus d. Here I already recognize that this is d of phi dot phi minus 1 x, and I recognize that this is u at x delta phi minus 1 x. So I'm only using chain rules. Then finally here I use same ideas but with dot instead of deltas, right? And I get delta phi minus 1x minus, I'm writing the answer minus plus z delta phi minus 1 x u x minus d u x delta phi. So I'm recalling what I'm doing. I have some variations of the configuration map phi. I'm writing u as phi dot composed with phi minus 1, and I'm computing the variations induced on u from variations of phi. So I'm taking epsilon derivative of this expression, I get this. I recognize u here, the original velocity, and this piece here, everywhere. This is completely arbitrary because this is built from arbitrary variation of phi. So I'm free to call this guy u of x. So the conclusion is that delta u is dt u plus d u minus d u. Okay. Now I'm doing the same game for the other variable. So I'm taking the epsilon of rho phi, rho 0, right? And what I get, no surprise, is minus d rho d. So conclusion. Hamilton's principle in material coordinates is equivalent to this principle in spatial coordinates. Not for all delta u, delta rho, for delta u of this form, and delta rho of this form. So example, And back to the example of the fluid, right? And a computation shows that this variational principle with spatial representation is equivalent to the equations of motion. So, what I'm doing, I'm taking variations of this expression relative to u and rho, but using only variations of this type. Now, you can ask, what happens with C? I neglected until now if I include the finger deformation tensor phi C equals push forward of G. So this is an interesting object, right? I have to remember you that this tensor field is given like this. Right? This is the definition of the finger deformation tensor. It's the push forward to the spatial representation of the given metric tensor on the material picture, with which you can always choose to be delta ij if you want. So delta Cij is computing by taking the derivative of this object relative to epsilon variations of phi, right? So the epsilon equals 0 of this expression.
This I should be a J in the finger deformation tensor in your second.
Yeah.
Yes, in the line below, it's delta xj. No?
Yeah. Thanks. Small j. So it's a direct computation, and what we get is minus dk Cij dk plus ckj I plus C I K D J K. Where, as before, V is delta phi composed with phi. So in differential geometry, this equation simply reads delta C equals minus LB C. This is the B derivative of R, covariant, symmetric to tensor. So once you have chosen the nature of this C, for example here a covariant symmetric to tensor, you have no choice for the variations allowed for C. It's given by this. You cannot change this, otherwise you break the geometry of the problem. And correspondingly, the equation, the associate equation of motion is, so here the equation you have to add to your system if you consider C is this one.
Okay. Do you want me to say how C appears in the motion equation and then end as soon as possible?
And where?
So if the W depends on C,
Yeah.
okay, then the Lagrangian changes a little bit. Right, okay, like that. Or maybe just indicate in the motion equation how that changes the first equation in the motion equation, and then finish up.
Yeah, okay, I don't have the correct expression. It's quite important. I have to
Okay.
compute.
Okay, fine. All right.
Yeah.
So there will be another term in the motion equation.
Yeah.
That depends on C, the gradient of C, and dw dc.
Yeah, to simplify things, I can say this is a shortcut, that what you will get here is V sigma and sigma is GW dg. But if I'm saying this is really going very fast to get to this, because here I use the material framing difference. This is Doyle's and so this is an answer, but this is not explicit enough. There are many steps to get here to understand why derivative with respect to rho and C suddenly disappear and you are left with this one. Okay, I'm done.
We have 1 minute for questions. Any questions?
Okay. Can you write down the also associated Hamiltonian? So at the beginning of previous lecture,
Yeah?
you defined Hamiltonian associated.
Right. So Hamiltonian will be defined this way. So we have U, L, U, rho C. We define M, L, U, and you have your Hamiltonian like that. L, N, U minus L, U, rho C, where U such that so here basically you have the same thing with the flash. So this is a simpler example.
Okay, let's thank Francois once more and have P until 5 after 3.